All right. Christmas Eve. Day 24, Arithmetic Logic Unit. Magic Smoke. Because the like of Dijkstra and A-star are still foreign to me, the simulation was easy, but the solution was hard, and solving it by hand. Yeah. I was gonna try A-star, but I can't be bothered now. I think it would be a lot faster than Dijkstra for that, because there is an imbalance with D. Like, it heavily wants to prioritize minimal movement of D, whereas our algorithm is not really caring. But A-star would care a lot about D and C. Magic Smoke. Something. Electrical engineering smoke, okay. I've never heard the term magic smoke. I've done a bit of electronics at school, but not professional electronics, so. Post hoc ergo propter hoc. I feel like I should know this phrase. Post hoc ergo. So after, therefore. Yeah, I mean, in mathematics we've used phrases similar to this, but I've not seen that phrase exactly. Propter hoc. After this, therefore, because of this. Since event Y followed event X, event Y must have been caused by event X. So it's sort of like a causation versus correlation type of fallacy. But a bit simpler. It's not quite correlation. It's that happened, then that happened. Brazilian footballer Pele blamed a dip in his. Alright. Vaccine adverse events. Yeah, that's a pretty big case for post hoc ergo propter hoc. Alright. Starts leaking from the submarines. ALU. Without the ability to perform basic arithmetic and logic functions, the submarine can't produce cool patterns with its Christmas lights. It also can't navigate or run the oxygen system. Don't worry though, you probably have enough oxygen left to give you enough time to build a new ALU. The ALU is a 4-dimensional processing unit. It has integer variables w, x, y, and z. These variables all start with the value 0. The ALU also supports 6 instructions. We got imp a, reads an input value and writes it to variable a. Add a b, add a to b, store in variable a. Multiply ab, multiply a by b, and store the result in variable a. Div ab, divide the value of a by the value of b, integer division. Truncate means to round the value towards 0. What does Python do by default? I mean, are we even working with negative numbers? Yeah, probably. I never even thought about that. towards 0. Yeah, that actually aligns with what I would expect. Okay. Mod AB, yeah, okay. Equal AB. If A and B are equal, then store the value 1 in A. Okay, easy enough. We don't have a whole bunch of others where we do pass by reference, pass by value, etc. In all of these instructions, A and B are placeholders. A will always be the variable where there's... Okay, fine. Or B can be either a variable or a number. Oh. Okay, so we do need to have some sort of inline method, which... Yeah, okay, that's easy enough. The ALU has no jump instructions. Okay, makes it simpler. Okay. Once you have built a replacement ALU, you can install it in the submarine, which will immediately resume what it was doing when the ALU failed, validating the submarine's model number. To do this, the ALU will run the model number automatic detector program, Monad, your puzzle input. Alright. There's no jumps. Model numbers are always 14-digit numbers, consisting only of digits 1 through 9. Digit 0 cannot appear in a model number. When Monad checks a hypothetical 14-digit model number, it uses 14 separate imp instructions, each expecting a single digit of the model number in order of most to least significant. So you would give 1, 3, okay, fine. When operating Monad, each input instruction only ever be given an integer value of at least 1 and at most 3, 9. Okay, fine. Then after Monad has finished running all of its instructions, it will indicate that the model number was valid by leaving a 0 in variable z. However, if the model number was invalid, it will leave some other non-zero value in z. Interesting. Okay. Monad imposes additional mysterious restrictions on model numbers, and legend says the last copy of the Monad documentation was eaten by a tanuki. This is the Japanese raccoon dog. You can, there's actually in the game, video game, what's it called? Shadow Tactics? Blades of the Shogun. One of the characters you can play as a tanuki. You can like send your tanuki to distract guards and then like assassinate them. I never saw one when I went to Japan. I don't know if people actually walk around with them. I don't think it's the kind of animal you actually walk around with. It's not really a dog, is it? It's a raccoon. They probably have them at events or something. What's it of the order Carnivora? Which is... wait, Canidae, which is... quite close to dogs. Alright. Oh yeah, of course, the Tanuki suit. There we go. You'll need to figure out what Monad does some other way. To enable as many submarine features as possible, find the largest value 14-digit model number that contains no digits. What is the largest model number accepted by Monad? How many possible numbers are there? It's 1s and 9s, so it's like 2 to the 14. That's what, like 8,000? Number of instructions is that, and there's no loops, so it should just be pretty straightforward to just try them all. You can start from 9999 and work your way down, but I think I even need to. All right. Alright, so... okay, so the first instruction is imp. Oh, no. And that has, several imps in there. Okay, fine. So we can just say instructions. Okay, so let's just do a split. I guess just put the tuple in, but let's say we put a none. Let's just make it 3 variables, just easier to unpack. So if so tokens tokens 0, tokens 1. We don't actually want to int anything. We'll just do that. Else install tokens. Let's just do that. And then so we want to define running running monad, so running a script on a given input. Okay. So okay, we'll just call it num. Might as well be a string, not an integer, because we're sort of feeding digits in. So let's say num index equals 0. And then we have to set the variables, so they said I've got a dictionary here. Variables equals w 0 0 y 0 z 0. Is that everything? Yeah, Z is used for the output. Okay, then we just have to do a... How do you do Python switch case break again? Okay, so we go for... Let's call it instructions. Instruction, or actually let's call it ins 0, ins 1, ins 2, or I think it makes more sense to that's fine. All right. In instructions, I don't remember how to do this switch case break thing. Python switch case match. Okay, so match ins O case imp. All right, so if it's imp, we do read an input value and write it to variable A. Okay. So variables, or variable, let's just call it variable. int1 equals int of num index, and then just push num index forward by 1. Okay. Add. Alright, we need a little inline method here. In a local function here. Get val if k dot is digit, return int k, else return variable k. Okay, so we get the value or by reference. All right, so case add variable int1 equals and then this pattern is roughly the same for all of them, so let's just copy this a bunch of times. So this is mul. Yeah, I don't see any way we can go negative anyway. Mul equals that times div that mod that equal, so it's going to be 1 if A and B are equal. Basically that. Okay, that's right. That is how to run the program. You can just try all possibilities. So how do we do this? We just want to. It's gonna be iter tools. I think for the next part they're probably gonna make it longer. Make it a longer string. From iter tools import. Oh, I always forget which one's which. Cartesian product, isn't it? Product. Gonna be 191919, so or R in product. It's gonna be 9. Four. Does that work? So that's an iterable. It just takes the first character and the next character. Print this. I just want to see what it looks like. That's not right. Okay. How does this work? I forgot how product works. I have to go online. Hang on. All right. ITER Tools product. Oh, I see. You don't do that. We don't. If I wanted to do this, I would have to basically do that, and then do like star whatever to pass it in as an argument. Except I don't need to do that because you just use cycles equals 14. Wait, what was it called? Repeat equals 14. There we go. Okay, so then the string, the imp will be join R. What were we trying to find again? Best largest model number accepted by monad. Okay. Largest equals 0. If we didn't do anything with this, define run, and then we return true if 0 is in Z. Okay, so return variable Z equals 0. There's no like loops or things like we often have in those int codes, so it's just like a one pass thing. Alright, so if run imp, let's call it num to be consistent. If run num, largest equals max largest int num, print largest, go. Hang on, what happened here? Not enough values. Expected 3 got 2. Did I not put... Oh, that should be imp, not ins. The error -8. I got a negative number? Oh, you do have negative numbers. Okay. Okay. So we can just do a little hack here. The proper way should really to use regular expressions or something. but you can just say if k last character is digit. If k is a last character. Zero. Huh. 1, 9, 14. Alright, I might not have used the right things here. Submarine model numbers are always 14-digit numbers consisting only of digits 1 through 9, not 1 to 9. Oh, that changes things. That actually makes it easier. And then we just count down from 99999. Which I could have done anyway with that approach, but I was just cutting corners. But we just have to watch out for digits 0 appearing, so... Like, it's a big number. So it might be a long time until we actually find one. You can cut out a lot of work by skipping the zeros when you're counting down, but that means you have to write your own decrement method, which is not too hard. Okay, let's just try for R. How did I end up thinking it was 1 or 9? Yeah, no, it wasn't. It's 1 through 9. Okay. I have a feeling they want us to actually figure out what this is doing. I mean, it's only... It is 100 instructions, so being able to reduce it to like 3 instructions would actually be save time. But anyway, let's just try. So for K, I don't know why I want to call it K now and not R. K in range. Right, well, we just break. I don't know if this is actually gonna work. Okay, so so if run. Okay, so if run. S equals string of num of k. Well, num equals string of k. If 0 in num continue. If run num print k break. It's gonna take forever, isn't it? We can get a sense for how many we're getting through. Alright, we need to what actually affects the Z? Oh, the very last instruction does affect Z, so we can't just stop early. They're not going down to 0, the number has a constraint you missed. Well, I mean, I know that's not a valid number. It wouldn't matter because I don't expect to get that close anyway. I can put smallest value viable number, which would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Put 0 there technically, but I don't expect it to get anywhere close anyway. Looks like we're actually gonna have to do some thinking about this, what's actually happening here. Well, I mean, it is a linear pass, so it's actually you can just figure out what this actually ends up being. Interesting. So the Z is only when we... Okay. How many times does this come up? 14 times. So we do 1 for every digit. So it's actually sum of the Y's, each of these. And they're independent. Are they? Multiply x by 0. By 1. Yeah, it looks like it refreshes them. We'd have to check each one by one to confirm that. But then that simplifies things. So in order for Z to be 0, every single one of these should return 0. That tells us what each of those digits would be. Okay, stop running this. Do we do this by hand? Okay. No. We can just well, I should have a quick look and confirm that that is actually true. X is initialized as 0. Oh, hang on, we're playing with Z. Why are we doing that? Divide Z by 1. Okay. Multiply Y by 0. Multiply Z by Y. Oh, okay, it's not actually that simple. So we always end up multiplying it by Y and then adding Y. In order for all these to be 0, we... Oh. Yeah, but Y could be negative. So it's not actually independent. We can't just make all of these 0. It could be that Y becomes a really big negative number. Well, looks like I'm gonna have to actually figure out what each of these are doing. Can we confirm at least that x and y are initialized every time? Yes, looks like it. Let me separate these properly. So x is 0, y is 0. X is 0, y is 0. Why does it do div z by 1? Strange thing. Alright. 0, y is 0, okay. 0, y is 0. Okay, so x and y safely start at 0 every time. Yeah. Okay. That's useful. And then Z. Yeah. Div Z by 1 is just a dummy operation, isn't it? It's not actually doing anything. Okay. So the actual only operations we do for Z is at the Y's. It's really a case of building a Y using... What does W get used for? Alright. Okay. So if we could figure out the 14 Y values we need, then that would then you would just reduce to solving those independently. But I guess we need to find out if Y is always positive. Because if it is, that basically turns it into independent problems. Let's have a look at this. Right, as long as we're not using negative numbers, the moment we use a negative number, then the numbers can be negative. So far those are all positive. Okay, add x minus 8. Interesting, so that turns it positive again. So that means we're back in the positives. Okay. Again, it's safe because this becomes positive again. Is this the key? Is this basically the number we want W to be? Not quite, but I think that we're basically there. We're almost there. We just need to... Okay. So we've confirmed that these are now fully independent problems. All the y's have to be 0. So... this should really just be 14 separate programs, right? And when we see the next imp, we create a new program. Let's just try and code it that way. And then we can just try 9 different numbers to find what makes it 0, and then once we know all the there may be multiple values that do that, then we have a Cartesian set. All right, let's see what it looks like. All right, so let's call it programs. Alright, so we go program equals that. If we've got an imp, then we just do this. Oh, why do I? Okay, we don't need that. Programs dot and empty list. So that's the new program. Do programs last one, append that. Else programs the last one, append that. It's all going to break now. Let's just look at programs. So we should have 14 programs now. Okay. Now, for I in range 14, we need to make Z 0. With so it still this program still returns, yeah, still returns that variable as is. Okay, so we want I program program. Hang on. Let's call these solutions. Or program in programs. Solution is an empty set to begin with. For I in range. It's not allowed to be 0, so it'd have to go 1 to 9. If this has to come afterwards. Run so this time this says we have a program and a W. So we'll just put W in there. X is 0, Y equals 0, Z is 0. No, we don't have that anymore. Put that. In fact, we don't need the imp W. Take that one out. Okay, take that out. And then match. So we take that out. This. Yeah, but we'll pass that in as an int. And then the rest is all fine. And if run I just had a look at my code and I remember why this was day 24. A problem that looks simple but requires proper analysis. Yeah. Well, let's see what part 2 is gonna throw at us. I feel like this is correct. It looks independent. If run I solution dot append I it run program I. So then what we should have is just a bunch of allowable values for each of the digits. And you would just take the biggest of all of them, wouldn't you? And we got 0 solutions. Okay. Why did I put... Oh yeah, because I didn't append the solution. Wait, is this... Hang on. Maybe my assumption here was wrong. Wait. We're adding the Z. Oh, damn it. I didn't even notice that instruction. That changes everything. That means we're carrying stuff forward. So we have to work backwards from the last program then. We have to say we need to know what. So the Z from the last one gets put into the X. Okay. Is that always the case? Yeah, it looks like it. So X is set to the last Z. So we need to know what pairs of values, the W and the X, the Z actually, would solve this. Work backwards from there. The last one we want to make Z 0. Let's just try running that last program, see what actually happens. Um, say for W in 1 to 9, Z in Z could be anything. It'd have to be positive, but what's the worst it could be? I don't know. Let's try 100 for now. That should be a range. If so, okay. So okay. So the program actually needs a Z, and Z set to Z. And we want the Z to end up being 0, at least for the final one. Okay. Let's just see what this final program, if run, would be programs -1 WZ. Let me just print WZ. Let's see what happens. 1728. Hmm? So, um, fine. Well, that's nice. Okay, so it's saying that Z has to be uh, W plus 6. I shouldn't manually do these one by one. I should, okay, so how do we do this programmatically? Basically have a table of values. This 100, I just pulled it out of nowhere. What is the could there be multiple? No, because it's a linear expression. Well, it's not linear, but it's an expression. An arithmetic expression. Um, so we could just do this. We can just say okay, so we have a way of figuring out what Z is needed for a given W. Now, this is the rightmost program, so it's actually the least significant bit. So we need to take biggest. Oops. I mean, what this tells us is if we're carrying forward 7, 8, 9, 10, 11, 12, 13, 14, each of those, then there is a W, the last digit, that will force it to be 0. So that gives us an allowance. Is it always going to be a linear range? Because if so, that's good. So then we could just work backwards and say, okay, given so we're saying the last program has to have returned Z equals each of these, and in each of these cases, we know what W will fix it. All right, okay. It's starting to come together now. It's confusing though. Okay, why don't we just try and compile all these programs one by one? So, starting from the end and working backwards, we always have a target set of z's. In this case, the target set is purely just 0. And that target set grows as we go back through the programs, as in the allowable z's. How do we do this? Okay, so for program in backwards. So we start off with target equals 0, I guess. So we basically do this, we say for each of the W's we could feed into this. I'm getting confused now. What am I actually trying to do here? We're not trying to maximize the W's as we go along because we care about the biggest W right at the back. Okay. So we don't actually... Okay, this is not... Get rid of that. We will actually return the value here. Run. Returns that. Okay. If... So W... Let's just make a map here. Needed W for... Wait, do we care about which... Well, okay, that's not an if statement. Okay, so... Make this a set. If run programs in target that means, okay, that we can hit our target. Then we want the Z to be the new target, basically. So this Z is the one that came from before. And that value is what we need. But furthermore, we know the W we would need for that given Z. I guess we can put that somewhere as well. W needed for Z equals that. More. Now we have a new target set. What are we doing with this? Just put it in a list. Maps equals list. Put it at the front. Let's just run that. Be 0. And then I just want to see what this looks like now. No. Maps. So it's saying this first map is saying we can either go with 189 or we can go with 0. W we need for each of those is 1 or 8, and each of these will lead to a final 0 if we follow the right path. So if we pick the 8, then we'll pass a 0 on. Wait, no. We have something in front of us. I'm just not clicking for me now. Hang on, if I change this, could there be multiple? That's too big. I don't think I can. Oh, interesting. Okay, fine. Alright. Let's half get it. I think I need to think this. I think this is going to be another case where I don't finish today. I think I need to think this over again. I need to get some pen and paper out. I can't just look at code for this one. But I can half see what is needed to be done. I just can't put it in the right order. I mean, could we run this? Could we do it recursively? Actually, it probably won't be too hard, will it? We just say, actually, yeah, I think if I write this recursively, it actually is much easier. Let me try and do that right now. We want to find the biggest Alright, let's see. Define get solve by hand for my data originally, then went back and solved by an input. Yeah, that's tempting. I think recursion will work here. There's only 14 things, so I get biggest W that will eventually lead to 0. That can eventually lead to 0. Okay. And we're given an index because that's what program we're looking at. And we know what the base case is. It's the final program. Given that Z has been passed along this program. That's what we want, right? We want this general function, given an index, i.e. which program we're looking at, and Z, that number Z has been passed in. We want to get the biggest W we can feed in as input that can still allow us to get 0 by some combination of all the remaining programs. So if we can solve this recursively, then that will then give us the correct digit for this one program, and then we push forward. And if we memorize this, am I thinking about this correctly? So let's see. So we just try all W's. For W in range 1 to 9. Result equals programs index to we run programs index for that given W and the Z that went in. And then we have to make a recursive call to the next one. So we say if we don't find any solution, okay, so largest equals none, and we try to find one, leave that blank for now. If largest is none, then we return so the idea is now we call if get biggest W, we now call the next one. I haven't done the base case yet. But this given Z is not none. That means it's possible to find the combination for that one. Then we found biggest one. I mean, shouldn't we just work backwards? Because we don't actually need to do all these steps. We can just say, because the moment we find one, then we're done. In range, so starting from 9. If then we return W. We found the biggest W that works. And then if we get to this point here, we just return that. Yeah, that's better. Okay. But if index is length of programs -1, that means we're in the final one. We want well, no, we don't do that. We say or W in range blah blah blah, result equals that. If index is if we're in the last one, then return at so there's two cases. Either it's the last one, in which case result has to be 0. If result is 0, return W. Otherwise, we try the next W. Is that all right? And if we're not in that case, then we just do that. And of course, we have to memorize so that we don't repeat these. And then let's see if we can get the first W. So we want to do get biggest W 0, and then the Z is going to be 0 by default for the first one. How long is it going to run? It should. Well, the problem is Z is a kind of an open-ended number. It can take a lot of values. It might be that we have to crack the actual pattern here. Apparently there's a lot of Z values. Hey, wait. Hang on. Get rid of all this as well. Look. Yeah, that was... I don't know what I was doing there. Alright. Get rid of W. Right, if we manage to find an answer to one of these, just like print index, I guess, I don't know. I don't think this is the right approach then. I think we do have to figure out the pattern. It's too many Z values. And the final thing was just like, Z just needed to be like W plus 6 or something. Oh, because it's the modulo operation that really changes things, because that's a many to 1. So is div, but... Let's make sure we can actually get small. I don't know, like 12, start from 12. Okay. Go for 7. Further back. Okay. Okay, biggest W. The answer to that is 9. Back to 4. What? Why is it running so quickly for these? I don't understand what's going on. If I go to 0... something strange is going on. Alright, so that's the... That doesn't make much sense. It hangs for 0 and everything else is just instant. Also, the numbers don't look right. Like, what? Why is this... Why... Like, we got 12... No. W in range, 9... X is always set to Z. And Z gets set back to... Huh? What does this mean? So it's... X and Z are the quotient remainders of dividing by 26. Oh, okay. Oh, I see why it was quick for these, because we were putting 0 in. So it's really easy to do when you push 0 in. But for the first program, Z is 0. The others we're just kind of setting X to always be 0. what's special about this number 26? Is this like number of characters? The alphabet? Interesting. Okay, so basically this method may well technically work, it's just too slow. The correct answer we'd get would be if we did W the first one and 0. So that would give us the correct answer, it's just it won't run. Okay, fine. And we can't just increase this to 1 or something because the Z would no longer be valid. Okay, fine. How far does it manage to get then? Like, let's print index. How deep are we getting into this? It's going to print a lot of indices though. Wait, what? We get all the way to the end. But we often... Okay, fine. So we go all the way to the end. But we're not hitting our target. I see. Alright. So the recursive approach doesn't really work because there's just too many Z values. I think we just have to work out what this program actually does. One second. Alright. It might actually just come out to be so simple if I just look at it for a bit. So, let me just try and write out what is happening here. So we've got X is Z. So when we first input W, Z is 0. Well, we'll just keep Z as a variable, so Z. X is set to Z. We'll just... copy these instructions somewhere. Okay. Right. Zoom out a bit. Alright, so... Alright, we'll just do it above. So we say... X equals Z. Alright. So get rid of that. Z percent 26. Z is now Z divided by 1. Just keep that in there for now. This one, we add 14. Equal X to W, so So if W matches that, so basically it would have to be Z would have to be above something. And to begin with, Z is 0. So X would be 14. So W would have to be... Wait, what? Well, I mean, it depends what we actually do with this. Okay, so this X is now basically W equals that. I should use colon here. The equals is a bit confusing. So X is now that formula, basically. And then we say if this is equal to 0, so not equal, basically. I see. Okay, that makes more sense now. And then Y is 0. It's 25. Y is 25. Okay, so we don't deal with X anymore. So now Y is basically 25 times that. Okay. Okay, we don't care about X anymore, I suppose. Oh, we do. And 1. This is not making anything clear to me. What is going on here? You've got two cases, basically. W... Yeah, we should just split it into the two cases, where W is this and W isn't. Say case 1. W is that. which it can't be to begin with, but let's just see what the formula is unfolding to. So then in this case, we are looking at zero there. And that becomes a 0. Y becomes 1. I need to make sure I'm keeping track of which instructions we got to. So that is case 1. Case 2. X is 1. Y is that's a 1. That's 25. Y is 25 plus 1, 26. Z is Z divided by 1. So those are the two cases. Then just look at the next step. Multiply Z by Y. Okay, so it's going to be... Just keep the 1 in here just to help me see what's happening here. 56 times that. Then Y is set to 0. And then add W to Y. Okay. And add 12. Multiply Y by X. Okay. So that is 0 in that case, and that in that case. And add Y to Z. Interesting. And like when Z is 0, that becomes 1 plus W plus 12, so W plus 13. And then that becomes W plus 12. W plus 13, W plus 12. Wait, no. When Z is 0, it's W plus 12 either way. Okay. So the first program adds 12. Oh, bad. I don't even know if I did that right, but Okay, that's sort of what it looks like. Okay. Now let's try program 2 because this time Z will be a variable. It's gonna be really similar, isn't it? Okay, so we have X, Y, we've got Z, which is passed in. Alright, so X is set to 0, X becomes Z. And then percent 26 divided by 1. Alright, so it's basically always the same pattern, but there's just some numbers that change, aren't there? I need a spreadsheet. I need to put these side by side. Or the spreadsheet. I just want to see which numbers stay the same and which numbers change. It looks like I think this is all going to come down to giving us an alphabetic message because there's 26 characters. But these are the that doesn't matter right now. I want to stop. Well, I'm still on part 1, so we're not close to finishing this. Look at this again. So, okay, so this was divide Z by 1. This was divide Z by 1. This is divide Z by 1. Now it's divide Z by 26. And then divide Z by 1. Divide Z by 1. Divide Z by 1. Divide Z by 26. What? It's always 1 or 26. Whenever it's 26, we seem to be subtracting. Oh, everyone loves int code. Yeah, I think the next step is I need to open up a spreadsheet and look at these. I just want to see them side by side. That'll help me see what's going on. Yeah, there's a very clear and I want to confirm that every instruction is the same in each of them. Can we do this within the IDE? I suppose we can. Whatever, I'll figure it out next time. I don't think there is really a... I think it's one of these problems that doesn't have a proper code approach. Like the final one, we want to make that 0. We already established that you have to add 6 to a W or something like that. Yeah, when it's a... Alright, worry about it next time. Okay. That's it. Tricky int code problem. It was the only one of this month. Unlike 2019, 2 years prior, which was like half int code. The year of the int code. So yeah, I couldn't solve it last time, and I mean, we're still on part 1. And but I think the thing is, I was trying to do a code approach, and it looks like we do have to... they're given a clue here. Monad imposes additional mysterious restrictions on model numbers, so I think we probably have to figure out what the criteria is for a successful model number. Like, it's probably some pattern. And go about it that way. So let me get my tea first. So we clean this up a bit first. So okay, so we've got a method which in theory solves the problem, but it's gonna be too slow. But the interesting thing is we can solve... We've got some interesting numbers here. 26, 1, 14, 25 that keep recurring. And what else was I gonna say? Okay, one thing we can do is we can cache this as well. Run program. Program index, say. Oops. So given a W and given a Z and given a program, just return the result. And let's cache it. So because we're making a lot of calls to it, I suppose. So if we cache both of those, will that actually help? Let's see how far we actually get. Okay, just having a think about. Yeah, so okay. Pirating it, see? Stop. Okay, what am I printing here? Printing W. Okay, just do that for the first index. If index is 0, W. It's on 9. But we're not getting any further than that. Let's wait and see if we actually get to 8. So basically we're trying all the remaining programs with all the possible values to find some combination that will yield how much branching is there? Leave it running for a bit. I mean, we've cached the program, so we don't call the program over and over again, but then again, it was just a few arithmetic operations, so it wasn't a big deal. Oh, we're not getting anywhere. How big do these Zs get? I'm gonna have a look at this. Is there an error? The approach to this was something I'd never written for. Interesting problem. Yeah, it does seem interesting. I'm gonna have to look carefully at the instructions, because I don't think I can just do this with code. Looks like there's an error. K-1 is digit. Or is it just because I interrupted it? Digit. So K. So when is it actually called? Get value is called on instruction 1. And 2. It's always called on 1 and 2. Wait, what? No, this is just where we interrupted it. Okay, it's fine. But the interesting thing is if I change this to 1, just go 1 program to the right, and then try again, we actually get an answer. That's odd. And that's how big the Zs get. That. So just adding that 1 more program suddenly what are we printing here? W's. Take that out. These are the W's and the Z's that would return 0. We're trying to keep them as big as possible, so it's like these are 9s, so it's always possible to do these ones with 9s. Well, no. It's always possible to do them with 9s if 0 is fed in, but I don't think it's going to be the case. Okay. It's such a strange program. Okay. I have to do what I did before, but try and write out properly what these programs do. But why is it so easy to solve any of these programs except for the first one? Like, what's special about the first one? Just highlight all of these. It has a similar structure, but that 26, 140. It's a very similar structure. It's just the numbers are changed. 1425. 1325. This one's very similar. So if I try 2, we are doing 2. 3. And for the last one, if you put 0 in, it can't be solved. So if you put Z in, it needs 4. Hello DJ, it is indeed int code time. Christmas Eve was the day of the int code. The only day of the int code for this year. Okay, so I found the pattern before for the final one, and it was just like a linear... Let's have a look at... Let's have a look at the pattern here. So for Z in range 100, let's say, print 13Z. All right, I want to see what values. So it's just that range there. So print Z. Okay, so for Z from 0, and when Z is 7 to 15. I don't know if there'll be any more down the line. Okay, fine. Well, we look at it, it's probably easy to work out. Okay, we won't worry about that right now. Let's try 12 then. What? Okay. Get biggest W. What? Now that's not right. W is supposed to be a number from 1 to 9. W in range from 9 down to 1. Oh, damn it. Stop printing things. Okay, there we go. So it's from 0 to 25. Interesting. Maybe I should be writing these down. Also, okay, we'll go to 1,000. We'll say R equals if R is not none, then Z R. We'll go back to 13. Okay. Let me just make some notes here, see if I can see any patterns. So for Z in the range 7 to 15, W had to be Z minus 6. Okay. 7 to 15, Z minus 6. Those numbers. There's a minus 6 there. That's interesting. Do I see anything like a 7 or a 15? Okay. Alright, fine. Let's try. Okay, let's try 12. So for 0 to 25, then it went to 8. What? So for 0 to... Zero to 24, W equals 9. 25, W equals 8. And then it went from 199 this kind of repeating pattern, isn't it? So it's like Z modulo on Earth. Look at the program. Is this? It's minus 16. They always do modulus 26. There's always a modulus 26, so that is a modular factor that they're interested in using all the time. 199 plus 26 is 225. Plus 26 is 251. What does this all mean? And why does nothing happen until 199 of the 25? I'm just going to have to write out the expression again and try and make sense of it. 126 divided by 26. And then this pattern sort of repeats. But only after 199. Okay. And then oh wait. And then after 415, there's no more. Because I go up to 1,000. So it kind of stops at. So it starts with a bunch of 9s, and then it's like 199 to 415. It's like Z modulo 26 minus something or other. Alright, let's go to the next one. 11. So now it's 0 to 25. Similar to before, but now it's 0 to 25, 9 is 9s. And then from 32... and then you got a bunch of 9s. And then this. And then to 1,000, there's nothing more. Oh boy. If we go all the way back to 1, it's the second program. Don't really solve it. Fine. Alright. Let's go to actually looking at the program. Alright. Start with the last program then. Alright, I'm not going to write this in the IDE because that takes me forever. Just scribbled something down. So we've got x is 0, z is z, y can be assumed to be 0, w is w, alright, so we start by setting x to 0, add x to z, alright, so x is now z. Mod 26, alright. Divide z by 26. Alright. Mod 26. They're trying to do like Euclid's algorithm or something. We've got the remainder, we've got the quotient. Is this like a common factor algorithm or something? Add x minus 6, okay. Check if w equals x. So this has to, I have to split this like a flowchart. So if w equals z modulo 26 minus 6. Yes, let me go to the left branch. So a no. Okay, so in the yes branch, so x will be 1 if they're the same. But the next line is doing x equals 0. So it's basically we're doing the inverse. All right. Okay, so x to 0, the other one's x to 1. Multiply y by 0, add y to 25. So y is 25. It might as well have started at 25. Now we do y by x. So in the case where w did match, that's y is just 0. And in the case where it didn't match, y is now just 25. Okay. Let me add 1. Okay. Y is 1 or 26. Multiply z by y. So in the left branch it will be z modulo 26. Z divided by 26. And in the right branch it's z divided by 26 times 26 again. So it's like basically rounded it down to the next multiple of 26. Interesting. Then y is made 0. Add w to y. So now y is w plus 5 now. And now multiply y by x. So 0 in the left branch, 1 in the right branch. Okay. And add y to z. That's interesting. Okay, so what this looks like, and I can write this down now here. There's just two cases. If w equals z modulo 26, but then multiply back up. Wait, no. Z minus 6. Then z basically changes to z over 26. Okay. Else z becomes z over 26 times 26 plus w plus 5. What the heck? So z is roughly the same, except it goes down a bit. Let's do this. Look, if w plus 5, because then we have a w plus 5 here and a w plus 5 here. That's interesting. All right. Now, for this program, none of this really matters. Z has to be 0. Wait, no, that's not true. Anything less than 26 would go to 0 as well. So in this branch here, that could never be 0. In this branch here, it can be 0 if z is under 26, but it also means this condition has to be true. So if z is under 26 and if it is under 26, then that is just z anyway. So w would have to be z minus 6. We already saw that from the data. For the final program, for z to be 0. Okay. This is going to bring us into like group theory, abstract algebra. So Z shouldn't grow that much. Like, well, but this is just the final program. We've got other programs that do other things up here. So this is program index 13, the final one. It's got a series of many to one functions. They're non-invertible functions. Let's just do the next program. I want to see what it looks like. Program 12. So this one here. So the number we divide Z by is always 26 or 1. And then we add a variable. And then these are all the same, W00. So, okay, let's look at how many variables we've got here. $25x1, y0w, y0w, and then there's a 9 here. So 25 is always there, right? Yeah. So really, the variables we have are this, which is either 1 or 26. So we've got the div z by... I'm going to have to give these variables names now. Let's say that's u. U is 1 or 26. And then we have the add x. Let's say that's v. V is always negative? No. It's always within, like... the range, like minus... minus 25 to positive 25. Something, I don't know. And then we've got that all stays the same, and then y always starts at 25. And we've got this one here. W. No, W is reserved. Okay, let's go with RST. And T 983 0, so it's like a small positive number. Oh. Right, well, it's always positive. It's like under 20. Alright, so what's the general formula here? Write this out. We could even replace our program with that, but we don't need to. I mean, it's the same efficiency. Alright, so if we take a general one of these, like this one. So we've got x set to like z. It's then 26, so it's... and then z becomes z over u. Okay. Add 14. So we add v to x. Then we check if w is equal to z percent 26 plus v. And if it is, then x will be set to 0. If it isn't, x will be set to 1. So we're here and set y to 25. And multiply by x and then add 1. So that will go to 1 and 26. Interesting, we've got this 1 and 26 coming up again. And after that line, multiply z by y. Okay. so Z stays the same. Left branch, and it multiplies by 26. So if we have divided by 1, then it's blowing up by 26. That's why these numbers get so much bigger. Okay. And Y becomes W plus W. Oh, no, not W. It wasn't UVW, it was RST. So Y becomes W plus T. Times by X. Okay, so it's either 0 or W plus T. And then we add that to Z. So the final thing looks like this, basically. Assuming the same pattern for all of them, it does look like that. It's basically program, so general program looks like this. If W equals Z 26 plus S, and S is like can be negative or positive. Then Z becomes Z over R, else, and these are the three variables kind of that change between these programs. And that's really all there is. In fact, we should probably reduce these programs to just that triplet. We'll do that and see if we get the same result. Alright. Third. Else. Z becomes Z over R times 26 plus T. Now, R is either 1 or 26. And T is just some small positive number. Okay. Well, at least we now know exactly what the formula is doing. And well, We want the final Z to be 0. There's a branching factor of 2 as well. Per program. What do we do with this now? So every step it either the value of W doesn't really, there's only one value of W that should matter, right? And the other 8 would be irrelevant. So if we want to stop this number from blowing up, we would have to be in this top branch every single time, because otherwise we can't get it to come back down again, can we? I mean, we technically can, but so that does reduce Z, and then we add W plus 5. So seems like the thing about the biggest W might have been a slight red herring, and maybe there is just one solution here. I mean, technically this can actually reduce it though. If Z was small, well. Reduce it a bit, but not much. Like, ideally, we just want it to be in this case all the time. But the thing is, this can never bring it to 0, can it? Well, okay, but we know that the final step can't bring it to 0, but we can bring it to 0 earlier on, and then let it blow up again, and then reduce it again. So that doesn't necessarily mean there's a unique solution. We don't have to have every single thing here. Like, we could just have a bunch of divide by 26 in a row towards the end to clear everything out. And these ones definitely we want to avoid if R is 1. How many R is 1s do we have? Put that one there, that one there, there, there. So I think so by the end we need Z to be under 26, and we need the W to be Z minus 6 or whatever. So in the general case, yeah, there's a unique value for W which will put us in this branch, and all the other W's will put us in this branch. Okay. Oh, how do we put this all together? Z starts off as 0. The one possible solution, yeah, but S isn't always in the if we tried to keep Z at 0 the whole way through, the values of S. So it was like, it can go as high as 14. Wait, okay, so for those ones, it's not even possible, is it? The W... If S is higher than 9... S is higher than 9, then, that's a no. It has to be this case. W can't be large enough. Let's have a look. 14, 10, 13, so -8, so that one 11, so quite a lot of them. Oh, very big, aren't they? -11, 14, so all the ones that are above 10, it may as well just... So we can say right from the start, if S is greater than 9, then it's this, essentially. No, then it's this. And the value of W is irrelevant. Oh, missed out something important here. Oh, I've missed out the plus W. That's quite important as well. That means the value of W does matter. Even... okay. So that doesn't massively cut down the branching. The value of W does matter. Okay, fine. I mean, for now we can translate that into a simplified program, which is literally just these 3 values. just do that. So from now on, let's say alright, for line and roof to lines to let's say program counter PC equals 0. PC starts at 0. And increases by 1. But when we get the input, we'll say PC resets to 0. But we don't need the... Okay, and the programs are just going to be triplets of values. So, need that. Like that. Let's say RST equals this. All right. So when we see one, two, three, 4. So R is this one. 4. RST, put that one in. If PC equals 5, I mean, it's just this. And then the final thing is this one here. 16. So T, 15. And then that's it. That's so none of this matters anymore. So define run. So the same thing as before. That we can run both of them side by side, see that we get the same answers. Define run. So this essentially. If, okay, so RST equals program index. All right. If W equals Z plus 26, I don't know how many parentheses we need here. Return that, else return that W plus T. We can try running these again. Okay. Programs and parts. We don't actually need that. Still Z minus 6. Okay, that's cool. Let's see what these programs look like then. Okay. I wonder what happens if we just try running this again. No, not this. The get biggest W on like 0. Would it be any faster? I don't think so. It's doing the same amount of work. Okay, so now what? Well, we know exactly numerically what it's doing now. So, okay, stop this. Oh, now what? It would have been better if I didn't have that W there, but then that was a mistake. The W does need to be there. But, because then there's only really two groups of W's that matter. But, okay, what? So towards the end, we've got a bunch of 26s for the R's. So I said earlier that if S is greater than 9, then this if condition is redundant, essentially. How does that help us? So if it's 9, then we're always in the second case. Doesn't mean we get to skip anything though, because we still need the W and the T and everything. It does probably mean W can be 9s for those, because like we're never going to be able to get it smaller, but that would still make this bigger, but what range? Okay. in the cases of the ones where R is 26, then we don't actually need Z as an input. We can just take Z percent 26 and Z divide 26, which means there's not an infinite possible number of inputs to the run function. It would just be that, I mean, that's significant. That means the recursive calls, if we're still going with this recursion thingy, don't need to call this. Like, we can actually call the second one, which would be Z mod and Z div. Or Z div and Z mod. That's like the order. And this only takes... Oh no, wait. Z div does take infinite values. Doesn't help, does it? Well, it sort of helps. Oh, I don't know. Oh, I don't know. What do we do? Let's do like some sort of dynamic programming. Well, that's what I was already trying to do, but not like that, but instead like nothing's really jumping out from this to me. Like, what is this? Does this mean? Is this some sort of... The T is that number there. key is 0 there. It's always a number under 26. If Z is under 26, then it may as well be 0. Get rid of this. There's a bunch of ones. So it's 1, 1, 1, 26, 1, 1, 1, 26, 1, 26, 26, and then it's 26s. What does that mean? We could say that if z ever exceeds a certain number, then there's no way to rein it back, and we should just abandon that particular value. So like we can say if you get to here, for instance, then all of these have 26 as R. So in the best case, they can reduce Z by a factor of 26. I mean, if R is 1, then Z strictly grows. So we can say for a given program, this could actually cut down the like the growth of Z, so that we don't go down paths with huge Zs. We can say for a given program, we want to get the biggest W, that index Z. Alright, so let's count how many programs have 26 in them from this point onwards, well, including this one onwards. So count 26 equals sum of, so P0 is 26 for in range. So starting from our index, ending on length of programs. So the number of 26s is the number of chances we have to reduce Z, and if we do, we'll reduce it by a factor of 26. We can reduce it by a factor of 26. So if Z, so in the absolute best case scenario, we would keep Z as is for all the ones, and we would reduce it by 26 for all the others, divided by 26. So if Z is bigger than I guess, so if it's bigger than 26 to the power of count 26, I guess. And that's not the symbol you use. So if it was exactly equal to 26 to the power of count 26, then we could divide it like that many times, and we would end up with 1, which is still not 0. So that's, so it has, if it's strictly greater than that, then we return none. So it's basically just cutting all the big Z's out. Does that help? See if we actually get anywhere with this. So can we... Oh! 3? That could be the first digit of the answer. Well, let's try it then. So we need to then... Does that cut down the branching sufficiently that it could actually do it? So for... So we actually need to return 2 values here. Okay. Result equals that. For I in range, because we're caching, so we won't have to repeat too much. So for I in range length of programs, so z will start at 0. So we need to change this to, when we return w, we spit out the z, that will actually it's cached, so we can call it again. So pair equals that, basically. Now we're just picking up all the W's. We know it's solvable, so this is never going to return none, hopefully. Equals so we can just assume it's so we just do hang on, what am I doing here? Wait, no, we don't do that. We do result. The result is the Z we get out of this. Yeah. Z equals that. So we get the new Z out of that. WZ result append string W, and then print dot join result. Oh, this might work. $3,999. That's interesting, because we noticed that just after that first one, like if I'd started at 3, maybe I would have got there faster. Let's try that. So if I just take that out, It doesn't really matter. It might have worked if we had fixed the first one at 1 and 2 and 3 and so on, just to... But clearly doing that did actually cut a lot of the branching out, because if Z grows just a few times, that's already, like, too much, that it can't come back down, can it? So, let's see. And the fact that we got anything at all, it's gotta be right. Like, otherwise, what have I just found here? Like, yes! Oh, interesting. I think there's probably a lot more to that program than what I understood. Like the only real fact I used from that program is the fact that it blows up by 26 or blows down by 26, and that's sort of a big restriction on the number of W's you can allow. Before it gets out of control. But there's all sorts of other weirdness in the program, so I feel like... Well, I mean, it's only part 2. We're not even done with the problem. Let's have a look then. Do I have time? I have a bit of time. As the submarine starts booting up things like the retro encapsulator, you realize that maybe you don't need all these submarine features after all. What is the smallest model number accepted by Monad? Okay. One would hope. I just have to reverse it. Does that make things... So this whole thing about Z blowing up holds the same as before. Like, it doesn't matter whether going up with the W's or down with the W's. Alright, let's try. Just, make another function here. Get smallest W, and for range 1 going upwards. That's all? That all holds the same. Is there anything about the nature of this that will somehow make this much worse? I don't think so. It's like a... So if W are small numbers, it's... I guess it's... less likely... It's less likely to get this to be true, so it's going to blow up more often. But that's not a bad thing, because when it blows up too much, we cut out early, so... I don't know, we'll just run it and see. Oh, it was faster. Yatta! I'm guessing then that people who solved it were pretty okay with part 2 if they had managed to do part 1. Yeah, that was the one I observed before. There was no trick to part 2. You literally just reverse the index, you reverse the direction of... reverse the priority. Oh, that was a really taxing problem. These encodes, they really make me use my brain in ways I haven't had to use since university. Like, this is original research we're doing with these encode problems. Yeah, very interesting problem. Ooh, good number of people actually did it. Well, it was the lowest out of any of these, but still. What was this one again? 19? This was the... Oh, yeah. Alright, well... I could actually finish the whole thing today. Let's take a look.